Okay, welcome. Happy Thanksgiving. I've gotten a couple requests for another video, so we're gonna go through it. I'm gonna have this video more of an example problem. So if you want, you can try it out before. I highly recommend doing that. But how it's gonna work is it's gonna be example problem, but I'm gonna break off and branch off and really try to explain things in detail. That's gonna make this a very long video, so I highly encourage you watch at 2 times speed or more if you can, especially on the parts that you know and understand. So, or you can skip to the certain parts if there is something that you got stuck on. Feel free to do that. But I'm going to try to go through everything that I think is useful and should help you out and maybe clarify things or explain why you were doing certain things. And that I'm going to do this example. So I highly recommend take a pause and try this. I will say the 17 and 20 is this distance and this distance. So, and then the 1 centimeter is obviously in between. Okay, so give it a pause and yeah, come back whenever. Okay, so last year, yeah, and I also say watch this on 2 times speed. I'm slow, I speak slow, so that kind of makes it normal speed. So highly recommend doing that. But right here, we're looking at a question about Jimothy, who tripped and fell, landed on a force plate while running to get a pizza cone. Rest in peace, pizza cones. And the force plate recorded a ground reaction force, and we see that GRF is down here, and it is 2,500 newtons. We get the following free body diagram, and it shows all the forces on his outstretched hand, which absorbed the fall. If we model Jimothy's wrist as a solid radius 3.7 centimeter cylinder depicted below, answer the following questions. So we see our nice cylinder here. And the first question is calculate the axial stress that occurs on the cut surface from S1 to S2. So basically axial stress on this surface. So I will say this question in total took me about 10 minutes to do, and that's including looking up some formulas I did not have memorized for inertia in part 2, where you calculate the total stress due to bending. But we're going to start off in all these questions. You start off, we want axial force. So we are going to look at our assumptions and system of interest. So we have already, and we know we do this for most questions, rigid body, the most important, static equilibrium, and you can have something like point force. Point force is where you're just saying they act on at a point, right? Which they do because they're depicted as nice little vectors. But first, we need to define a system of interest. These problems are nice because they give us the free body diagram, and we know we want this S1 and S2 as a system of interest. But I wanted to go over and explain kind of why and how we're going to choose that system of interest. So we know with that first assumption, rigid body, if we assume this whole arm, this is the humerus, so arm bone, right? So if we assume that the whole body is a rigid body, we're saying that it's almost as if we're freezing this entire arm, right? So like the muscle of the bicep and then also tricep are like counteracting each other and nothing is moving, right? This joint right here, nothing is moving up. It is all static and rigid. So if it's rigid, we pretend this is a piece of ice, and let's say this ice is just floating in space, and I apply a force to it. This is a solid piece of ice, right? This whole thing is going to move this way, right? This ice cube is going to move this way. But we assume static equilibrium. So let's make it more like that question where we have the force here. And if we have the force here, that's going to make it move in that direction. So what we've learned in class and understand is that force is going to want to make the rigid body move in the direction it's pushing, but we know that there's a full right scapula that's here holding it to a body, and so we know that there is some x and y force that counteract this force, right? And that's where we get that static equilibrium, because we know that if we say static equilibrium and we're only given this force, we know that there has to be another force there. And we know mathematically we can display it as sum of forces, right? We know sum of forces is zero because static equilibrium, and we know that F is not zero, so that we need to add some sort of other force in order to get it to be zero. So, same thing happens. That's when we choose the whole arm as the system of interest. So, if we get rid of this guy and we choose just the forearm, right? The elbow. And also the ulna's upside down. I know I used it from a different problem and just rotated it. So there we go. But if we choose this as the system of interest, again, we know it's going to want to shoot upwards. So we know that there's going to be some X and Y force at the elbow to counteract this force down here. Right? That makes sense, because if that wasn't the case, if these green forces did not exist, this guy would be, his elbow would be dislocating and his forearm would be shooting off of the body because it would be moving. We know that's not the case, so we know that there is forces acting here. Okay, that makes sense, right? That's from the elbow joint. The same thing applies. The same thing applies when we're looking inside the bone. If we make this our system of interest and we cut it halfway through the bone, we know that this, it's going to be hard to grab this. Yeah, we're going to move the image. We know that this section of the bone, this green section, is not breaking off from this yellow section. So if we have this green section, we know that that's not breaking off, that it's, the arm is intact. So we know, since it's not moving, that there has to be some other force, XY, that keeps it intact, not breaking from the arm. And these green forces in this case are called internal forces because they're not acting external like the elbow and stuff would on the bone. They are inside the bone. So whenever we're finding that stress, it's because there's internal forces holding the bone together, right? Because if we didn't have those internal forces, the arm would break because this force down here would shoot it off. So I hope that makes sense why we make those assumptions and why we can calculate forces on this surface. So these, because there's internal forces. So we will grab this second question. Actually, we'll just grab the image. And we'll paste it here, right? And then I'll also grab this guy as well, just so we have a reference. We want to find the axial stress. What does it exactly say? Calculate the axial stress that occurs on the cut surface seen in the model. So here, axial, we're just looking for the force that is normal to this surface. So we just want the axial stress. We're not worried about bending yet. So again, we can simplify this into something here. I guess it is a cylinder. Sure. There we go. We'll grab this, and we can simplify it to where we have sorry, man, my drawing skills are brutal right now. Okay, there we go, and we have S1 and S2. So basically cut it in half, and again, we know there is a ground reaction force, and we know that this force equals 2,500 newtons, right? We are given the orientation of it, which is 30 degrees, and we're also given the orientation of this bone forearm, which is 55 degrees. I'll draw that. 55 degrees. And we want to find the normal force. So we can start by drawing an NT coordinate system. I don't really care about T right now. We'll get this one out of the way, but we can have NT in purple, where N is normal, perpendicular, right? Perpendicular to that surface. Check. And T is going to be tangent to that surface. So basically, when saying axial stress, we want to get this force in this direction. Right now, it seems like it's pretty much in that direction. So yeah, I'll redraw this to be more 30-degree looking like that, and then we can drag it over. Okay. Yes. So we want to find this guy in the direction of NT. And just like we can break this guy into X and Y, right? So I'll draw it bigger here. We have this force. Just like we could break it into X and Y, or we can do it this way, where this is our Y force, and this is our X force, right? We can also break it in. If I get this here. Okay, there we go. We can also break it in to our NT side, right, by aligning these coordinate systems. And in this case, we would look and we could say that our N is going to be this vector, and then, yeah, T is about the right size. T is going to be this vector. Right, so these are the same thing. We're just so used to breaking it down into Y and X. You can do it in any perpendicular coordinate system, N and T. But we are given an angle here. We know 30 degrees. Here, we don't know. So how do we go about doing that? There's a simple tip that I think is an easy way of doing it. However, there is many countless ways of doing it. And I've had many times where I do it one way and someone asks, is this okay? And I look and I go, wow, I never thought of that. So There is so many ways to do it. As long as you get the right answer and as long as you're comfortable and confident doing it, there you go. But what I do is we notice we have two similar things. You just drag the vector, which you know you're given info about, and you also know, compared to the vertical, you have the orientation. So if we were to kind of color code this, yellow we see here on the top left of the screen, and then in blue we see right here. What do? You align them. Okay, so we now know this angle right here is going to be 55 because they both share this same vertical line, although it doesn't look, it should be. They both share the same vertical. 55 minus 30, because 55 is the full angle and 30 is this half angle. And so we know that this blue one equals, should be 25. We can double check 55 minus 30. If you're on an exam, you're not sure, always double check. I've made that mistake of just thinking I can do quick mental math, and clearly I cannot. So for a less colorful thing, we have two angles. We know this is 55 and we know this is 30. So if we subtract it away, we know 55 minus 30 is going to give us. Okay. So then that 25 allows us here, up here, we duplicate this guy. This one here allows us to solve. So we only want, I just keep jumping to that big eraser. We only want n. And so we have 25. So we know this, and I'll just draw it a bit easier. We know that this is n. We know this is 25 degrees. So since this is a right triangle, we know how to do that. We can go F. We'll do it in gray. Fn equals 2,500 newtons. And then we want the adjacent side. So it's cos 25 newtons. Will be the final answer. It will be in newtons. So doing that, we have 500 times cos 25. What are we given? We are given 2265.77 newtons. But this question wanted us to calculate the axial stress. And we know stress is normal stress, normal force over area. And we have this, but we do not have area. But we have the radius, which was 3.7 centimeters. So 3.7 centimeters, which we know area equals pi. Then r squared, we can do it into meters. 7 meters squared. And that is going to give us something really small. You can keep it in centimeters and do your units that way. It does not matter. Or you can do whatever you like. But yes, so we will pi times 0.037, the power of 2. That gives us something small. So we know normal is 2265.77 over top of, we can just drag this guy here. I'm not going to write it out. And that is going to give us something like 2. And then we can just grab that down there. And that gives us a big number, right? And why? Because we did newtons over meters, which is pascals. And we know megapascals is 10 to the 6. This is a whole lot of megapascals, or this whole lot of pascals. And if we see how many megapascals, we can just divide by 1,000,000, right? So we have 0.52, and we can just say 7 MPa. You can do little a to keep the TAs happy. There we go. How does that look? Okay, so if that unit conversion didn't make sense, what did we have on the calculator? We had, I'll just go over that one more time. 526,820.3 pascals. And we know we want 1 pascal on the bottom, right? Or we just know that 1 megapascal is 10 to the 6 pascal, right? And so we can cancel out, and we're left with megapascal, and that's dividing by 10 to the 6. And so let's hope that makes sense. I'll keep it on the screen. But let's go back and just kind of summarize what we did there. It can be scary. I will take this guy. I feel he's the most important. So we are given this situation, and this is just a force system analysis question. And right now we have sum of forces equals 0, and right now we have FGR. And we know that that equals 25. So we know that does not equal 0. So we know there has to be some other force, F, R, we can call I, internal force. Yeah, let's just call it Fi. Internal force makes it equal to 0. And that force, since we only have one, is going to be equal and opposite. So we know this guy should be the same direction, just opposite, acting up here. Right? Because if it wasn't for this guy, the whole arm would be moving in that direction. Right? So we looked for that force on that surface. And we found that force because it's the same. So we just projected that force. You can do either. We had our nice NT coordinate system, and we just projected. You could do the blue or the red. They're going to give you the same thing onto that axis to give us that nice N, Fn, right? And then from there, we used stress equals Fn over area. So it starts off by force system analysis, and then we project, and then we solve for stress. Oh, this yellow is blinding, but there we go. Okay, that leads us to our second question. So here we have to ask the total stress. And what does that mean, total stress? So I'm going to say it's total normal stress. So I'll put a little n there. And so what it's going to be is going to be our normal stress plus stress due to bending, or normal stress due to bending, right? And this guy is what we got in our previous question, because it's the stress that is perpendicular to that surface. But then we know that there's also stress due to bending. So let's kind of look at what stress due to bending is. I'm going to steal this drawing because I did a really nice job on it. Thank you. And with that, here you go. You'll notice, right, that right now, if I applied these two forces, that's going to send this bone, this body into a torpedo spin, right? So we know that the red, we have our point of rotation here. We know that the red force is going to cause a moment this way, right? And so we have this red point, this red vector doing a nice rotation here. That's what it's causing. And so we know that since, again, this bone isn't moving, it's not fracturing off, it is not bending and breaking in half from the rest of it, since it actually is still intact, that means there has to be an internal moment that counteracts this. Because again, we have static equilibrium. So moments equals 0. And right now, we only have one moment. And we know that won't equal 0. So that means there has to be a second moment, which equals 0. And in this case, it's simple because they're going to equal each other, because they're equal and opposite. So either this guy's negative or blue's negative. So we kind of get this moment equals this moment as our equation, right? And so we just have to solve for one, and then we find the other. And how did I know that this was your right-hand rule, right? If we have our vector and we kind of hit it up, we know, like, you can kind of simplify it. If we just had a log like this, and we had a pin in this log, and we hit it this way, that's going to cause it to spin around, right? But I actually don't know, and so we are going to calculate that moment first, because we know that stress due to bending equals mx over I. And I will go through x and I in a second and give some insight that you might not need to know but might be nice. So don't stress on that. But let's calculate that moment first. What do we first need to do? We can drag this guy here. We need to find our, well, we can do our moment equation. So yeah, with our moment equation, right, we are talking about moments, so we will go and do it here because we need a moment x and I, right? So here, we're writing our moment equation. We know moment equals rx fy minus ry fx. So let's snag this guy, because we want to make sure we have everything. So we can write it out. Rx equals 17 centimeters. Ry equals 10 centimeters. And then Fx equals 2500 sine 30, right? Because we want that top side, and then for y, we want that vertical side. So that y is going to be Fy equals 2500 cos 30. But am I missing anything? Yes, we forgot to talk about units. This method is very important. It is really the most important to talk about units. So here, how do we do that? Well, we can just align a coordinate system. We have F and we have R in blue. And if we draw our coordinate system here in X and Y, we can align them. Here, we notice that X and Y are both negative because the X direction is opposite way and the Y direction is the opposite way. Here, they're both positive. So, during that coordinate system, we see negative, negative, positive, positive. Always look at the signs before you start this equation. So, we can plug in everything. We have our x 0.17 times 2500 cos 30, right? And this is negative here. Minus, you can do both sides in brackets. Negative 0.1 meters, newtons, times 2500 sine 30 newtons. So there we go. And we can put this in the calculator with negative 0.17 times 2500 cos 30 minus negative 0.1 times 2500 sine 30. And we get negative 243. So this is again looking at this force here and the moment it's going to cause about this rotation. So we know that's solving for m. And we saw that was 243.06. 243.06. Just double check 243. And it's negative, which again is the clockwise rotation, just what we said. So it is this other side here. So with that being said, we know it is in Newton meters because we have our meters and newtons. But we want that blue one. So we know we plug it into this equation up here that we have negative 243.06 plus m equals 0. And so we know m equals 243.06, which again is the exact opposite. And so I always draw the moment on from the forces side. So I always draw the moment from the forces where you'll sum all however many forces in the moment arms. I draw it on this side of the surface, and then I know that the internal moment is on the other side. And this helps me with determining whether it is in compression or tension, because we see that on this side they are squeezing together. And again, you can think of compression as negative because you're shrinking it, you're pushing it together. You push a marshmallow, you're shrinking its height, whereas tension, you're elongating it, extending it, so you're making it longer. So you have tension on this side, they're pulling away from each other. So I draw it on there just to get a visual check. Now, I messed up the moment from the last one, so I already have this work out here. But, right, we have our moment. We just need inertia and our distance from that centroid. So, this part you do not need to pay much attention to. I'm just going to explain a bit of that inertia, that second moment of inertia, and that centroid point, right? So, basically, if I have a 2x4, right, just a piece of wood that is 2 inches by 4 inches and then some length, and I'm asked to karate chop it. Would I rather karate chop it like it's depicted, it kind of looks like a gold bar, or would I rather my friend rotate it like this and have myself karate chop it this way? Which one? Most of us are going to say neither. I like my hands and I like them in one piece, but you're going to say if you had to, this way. Well, one, this is a more narrow surface, so it might hurt the hand more, but it is also harder to break that way. Why? Because of this moment of inertia. Here, if we look at this surface, this object, this wood, is going to bend. So this side is going to be in tension, right? And this side is going to be in compression, right? So if we look at that cross-sectional area, okay, this side's getting squeezed together and this side's getting pulled apart. We'll just color coordinate it for you. And it is bending across this neutral axis. And this neutral axis is just saying there's no tension or compression because it's the middle, right? It's compressing more and more the further you get away from it. But as you get zero, and then it starts tension on this side. So here, right, the moment to this like surface is not as great. There's not that much material resisting on that axis. Whereas if we look here, right? We look here, that is a whole lot of material, right? Same thing. It's gonna bend, compress. That is a whole lot of material in this direction. In this direction, that moment is greater. So that resistance to bending is greater because it's further away from that axis, right? And so the further away that it gets, the harder, the more resistance it is to bend and break in half, right? So it's going to hurt and be harder to hit it this way. So that's all it's saying is when we look at that I value and we apply it to bones, whereas if I can draw a nice radius cross section, not really. We know if it's bending the neutral axis we somehow find through simulations is here. We know that it's going to have a different moment of inertia because there's a bunch of material spread out differently, but right, it's longer. It's like more elongated on this side where it's more stubby on this side. So you're going to have, depends on orientation, what that I is going to be, and mainly what that X, right? Here, that's a small x or a big X, whereas on this side, it's a small x. So sorry, when I was talking about length and size, in this case, I'm more talking about x, right? And so if it's an odd shape, beware that the x may change. You could technically, he could ask you to solve for something, they could ask you to solve for something in here. They'd just be solving for the stress at that mini little point. But we like these surfaces. Why? Because that's max stress. And max stress is going to cause a break more so than these middle ones. Maybe. I'm not a bone scientist. But okay, none of that you really needed to know at all. But there you go. The more information, power to you. Knowledge for the win. Here, we know 0 point. I don't know why it always jumps to that big eraser. 3.7. I'm going to lose it. 4 meters. And then we know that x equals 0.037 meters. So now we have x and I. We can solve for this moment due to bending. So equals 243. I'm not going to assign a positive or negative yet because I don't know if I'm looking for S1 or S2. So I'm just going to put in that value. 0.6. It is 0.6. Look at me go. Newton meters times 0.37 meters over pi over 4, 0.0374 meters for. And when we put this into the calculator, we'll times by 1, this times 0.037 makes it smaller, and divided by pi over 4 times what's going to be a very small number. Clicking around. There we go. That is big. Again, what units are we in? Well, look, we have 1 meter, 2 meter, 4. It's going to be 2. And then newtons. So we are in newtons per meter squared, which is pascals. And again, I don't like pascals. Little tip, I always did newtons and then millimeters for everything, so that I was always in megapascals, or whatever the megapascals unit is. But this way is simple, 10 to the 6. And we are back in megapascals. Equals 6.107 MPa. Right? 107. 107. No. 11. 6.11 MPa. There we go. Again, I'm making the mistakes so you don't have to. So, now we can snag this guy. I write real big. Hard to see. And we'll snag this guy. Or, sure, we'll actually draw our own because we are talented like that. There we go. Okay. So, we know this moment went this way, this moment went this way, and that we have an internal force acting this way, and this force which acts here is also kind of acting there. So we know this guy is going to be always negative, and we know this is S1, this is S2. Again, these guys are compressing here, so negative. So we know total stress S1 is equal to negative 0.527 minus 6.11 MPa. There you go, because they're pinching together. This side, they're pulling apart, so this side's under tension for bending. But again, both of them for axial is going to be negative. So then we have S2 equals negative 0.527 plus 6.1 MPa. Right? So there we go. And putting in these answers, I haven't rounded much, but 5, negative 0.527 minus, we'll throw this in full. It's going to give us 6.64 MPa, whereas this one is going to give us negative 0.527 plus 6.11, 5.583 MPa. So that was a very long-winded explanation on how to do this type of question. The way I did it was obviously a lot in detail to explain different topics. Oh, sorry. Negative and negative. Or no, sorry, positive. There we go. Negative and positive. Yes, tension, compression. But the way I did this question was long. How I would recommend doing a question like this is one, force system analysis, where you combine it into one. I broke it up because I was trying to explain things in a specific order, and because the question originally asked to break it up. But if you're given it, and let's say you're given F1, F2, you're going to solve for the reaction forces here, right? Whatever they are, and the moments here, right? And these two forces are going to have a combined moment on this area. And then once you have these blue forces, you can then do, once you have the moment, you can do stress due to bending. And once you have the forces, you can project into your NT coordinate system and do normal and tangential stress. But yeah, I would say force system analysis to solve for those forces. 2, you project for NT, axial stress, and then 3, stress due to bending. But yeah, hopefully that helped. If you have any questions, please let me know. You can comment them. I will do my best to answer them or make a video. And if you need a more in-depth answer key to this question, let me know as well, and I can send you one. But the answer key looks far prettier and better explained on paper than the video. The only good thing about the video is you get to watch me do the question, whereas some people like to just read it, and I've made a very big attempt in my solution keys to do that. But happy Thanksgiving. I'm thankful for the technology to share these videos with y'all, and for the 2 people who will probably watch this video. You heard. Have a good one. Cheers and good luck.